These are the solutions to your check-in on differential equations. Okay, here we go with our first page. Let's zoom in here a little on number 1. Now what I notice here right away with number 1 is that the denominator, if we take the derivative of the denominator, we will end up with the numerator. So let's let u equal e to the x plus 1, then du is e to the x dx, and that's some nice u sub. We end up with 1 over u du, which is the ln u, and that's ln of e to the x plus 1 plus c. And as a matter of fact, e to the x plus 1 will always be positive, so we don't need those absolute value signs there. So that is our answer right there. Moving on to number 2. Zoom in a little more. This here is of the form e to the u. So we'll let u equal x over 3, and we'll remember that that's really 1/3 of x, which means that the derivative du is just 1/3 dx. So we need a 1/3 in there. So we'll have 1/3 e to the x over 3, and we'll cancel that 1/3 on the outside with this 3. So that's 3 e to the u du, and the integral of e to the u is just e to the u, so 3 times e to the x over 3 plus c. So number 3 over here looks a little complicated because of all that trig, but it's not so bad because it's really of the form a to the u. So let's have our u be equal to the exponent, and you'll see that that u sub works out nicely. So that's the integral of 8 to the u du, and that is 8 to the u over ln 8, which is 8 to the sine x, sine x over ln 8 plus c. So now on to the integral of secant, and if you notice there are two next to each other that look very similar. We've got secant x and then the integral of secant squared. So they look similar, but they're very different, as the integral of secant is ln of secant plus tan. The integral of secant squared is just tangent. And if you remember, we learned this a while ago because we know that the derivative of tan is secant squared. All right, let's move to the other columns, starting with number 6. If I can find number 6, here we go. The integral of x tan x squared. So let's let u, let's try that again. Let u equal x squared. Then du is 2x dx. So what we'll do here is we'll stick a 2 in there and then cancel it out. So that we would have 1/2 tan u du. So this is just 1/2 ln of secant so it's ln of secant of x squared plus c. Now this next one has a typo in it. We're going to change the numerator. So instead of 1, we're going to cross that out and make it a 2x. Then it'll work out a little bit better for us. We're going to look at this as the integral of 2x over 1 plus x squared squared. So if we let u equal our x squared, we end up with that numerator, which is very nice. So we can write this as 1 over 1 plus u squared du, which is arctan of u, and then we substitute, and we've got inverse tan of x squared plus c. Now this next question looks similar to the one we just did. The difference is if we take the derivative of the denominator, we get the numerator, just like question 1. So here we're going to let u equal the denominator, and we get exactly the numerator. So this is 1 over u du, which is ln u, which is ln of 1 plus x to the 4th plus c. Okay, this next guy is put here really almost out of context, because this is not going to give us an ln or a trig function. This we can rewrite as the integral of x to the negative 3 plus x to the 1st. So to find the integral, we're only using the power rule. So this becomes x to the negative 2, negative 1/2 in front, plus x squared, positive 1/2 in front, plus c. And then this last guy over here, this is going to be one of our inverse trig functions. So this we can think of as, the integral of negative 1 over radical 7 squared minus x squared. So this is going to give us inverse cos of x over 7 plus c. Okay, moving on from our integrals, we've got some differential equations down here with number 11. We need to solve this differential equation with the initial condition that's given. So let's solve this first, or let's separate our variables. So we will have 1 over y dy equals x squared dx. If we take the integral of both sides, we'll have ln y equals 1/3 x cubed plus c. So our initial condition is f of 0 is 2. So let's substitute that stuff in now. We've got ln of 2 equals 1/3 times 0 cubed. So c is ln 2. So now we've got ln y equals 1/3 x cubed plus ln 2. So we have to solve for y. What we'll do is exponentiate. So we've got e to the ln y equals e to the 1/3 x cubed plus ln 2. On the left, we'll have just the absolute value of y. On the right, we'll have this, which gives us 2e to the 1/3 x cubed, let's try that again, 1/3 x cubed. And from here we've got to decide if we're going to have 2e to the 1/3 x cubed or negative 2e to the 1/3 x cubed. And we determine which one by looking at our initial condition. If we substitute 0 for x, we should get positive 2. And that only works with this guy over here. So not the negative. So that is our solution with the initial condition 0, 2. Okay, moving down to number 12. Number 12 is let's see, it's a growth problem. And what do they give us? We know that the population of the town starts at 1,000 people. So my children are being very loud, and it's occurring to me that I may have to wait forever for them to be quiet, so we're just going to deal with a little bit of background noise, possibly. So again, we're starting with an initial population of 1,000, and then they tell us that in 10 years, our population has increased to 5,000. And we have to write a formula that models the population of that town. And then we are going to approximate the population after 20 years. So let's start off. Here's our model. Y equals CE to the KT. And we know that when t equals 0, y is 1,000. So we've got 0k there. This means that C is 1,000. So let's rewrite our formula using that information. So we've got 1,000 e to the kt. And from here we've got a choice. We can solve for k or e to the k. If we solve for k, we're going to have some partial rounding in there. So we're going to solve for e to the k, and that looks like this. We put in our 5,000, and our t is 10. We'll divide both sides by 1,000. And then e to the k is 5 to the 1 over 10, which means that our model looks like this. 1,000, e to the k is now 5 to the 1/10, and that is our model. So now let's use this to predict the population in 20 years. Let's move the page over just a little bit. Here we go. Y equals 1,005 to the 20 over 10. And what's convenient about this particular problem is that when we solve for e to the k instead of k, we don't have to use our calculators. So this is 5 squared, which is 25. So we get a population of 25,000 people. Okay, next one is Newton's law of cooling. We're baking cookies, and we want to know how long it takes for our cookies to be 90 degrees. So what information do we have? Our initial temperature is 375 degrees. Let's see, it takes 10 minutes for our cookies to cool to 150 degrees. How long until the cookies are 90 degrees? So this is now y minus 70 degrees, that's our room temperature, is equal to CE to the KT. So here we'll substitute our initial temperature. So C is going to be equal to 305. So now our model is y minus 70 equals 305 e to the KT. So let's use the second piece of information, which is that our temperature is 150 degrees. After 10 minutes. So what is this? This is 80 equals 305 e to the 10k. 80 over 305. So e to the k is and that's the 1/10. Okay, so now y minus 70 equals 305 times 80 over 305 to the t over 10. So it's the model for the temperature of our cookie at any time t. And we want to know when the cookies will be 90 degrees. So we'll use the model that we created, and we'll substitute 90 in for y and solve for t. Oops, 90 minus 70 So 90 minus 70 is 20, and then we'll divide both sides by the 305. So we've got 20 over 305. We'll take the natural log of both sides, which allows us to bring the t over 10 in front. And then if we solve for t, we'll get that ln of 20 over 305 divided by ln of 80 over 305 times 10. And if I plug this into my calculator correctly, I get 20.358 minutes. And remember, we want to round to at least 3 decimal places. Okay, number 14 are slope fields. I love slope fields. And our equation is y over 2. So all we're going to do is take a look at the y coordinates and divide by 2. So let's see, the easiest would be when y is equal to 0, y over 2 is 0. So that's happening all along the x-axis. So all along here, I'm going to draw 0 slopes. And then when y is 2, 2 divided by 2 is 1, so we'll have these nice diagonals here. These are very sloppy. You're going to do a better job than I am. And then when y is negative 2, we'll have slopes of negative 1. Maybe if I can draw. My pen's not working. There we go. Sort of. There we go. That's better. Okay, negative 1. And let's see. Our slope will be 1/2 when y is 1, so not quite as steep here. Having some difficulty with my pen, but that is okay. And then for negative 1/2, again, not so steep as the 1/2. And there is our lovely slope field. Okay, number 15 is a multiple choice. We've got to match the differential equation with the graph of the slope field. So let's rule a few out first. Well, answer C. Answer C, our slope field, everybody should have a slope of 1, and that's not happening, so we can cross out C as a possibility. Now, if I look at D, I've got y squared. That means that all of our slopes should be positive, and it sure looks like that on our graph. So this is a good possibility. Whereas for A and B, those should have some negative slopes for when x or y are positive. So those are out, which leaves us with choice D. Okay, and our last question is which could not be a solution. So we are looking at which curves would not fit. Okay, so for this one, I'm right away going with choice A, because if you see here, we've got this curve happening here, and that is clearly not what our slopes are telling us to do. So choice A would not be a solution curve.